welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 37 today. In the previous lectures, we discussed about effect of multiplicity of indenters on pull of load. We considered indenters having flat plate or indenters having a concave shape. We also discussed about concave shape being spherical, concave shape being ellipsoidal, and we discussed about that when you have single load, single this indenter, what is the pull of load given an adhesion energy or adhesion strength at the interface. We talked about also crack propagating from the center, from the edge, and we discussed all that. And then we started discussing about this particular problem, that adhesion between two rigid spheres. So, remember that previously our discussion was centered on adhesives or indenters or elastic half space which are deformable. But now in this problem we started discussing that when these two into adherents, for example two spheres are rigid, they are not deformable, okay, then what will be the pull of load between them. So, what it means is that suppose you have this sphere and which is in contact with another sphere like this, both are rigid, and therefore, there may be so now you apply load, so they come in contact. So, if they are perfectly rigid, then of course, there is no deformation over here, but nevertheless there is adhesion between them, and so therefore, is attraction, okay, between them in the region that is outside this contact point or contact area. In some problem the situation may be something like this: we do not have exactly rigid sphere, because of the load there is a finite contact area that formed. Because of the load there is a finite contact area, okay, that gets formed, and this finite contact area that is formed is by the Hertz pressure. So, in the Hertz mechanics, okay, that suggests that when there is no interaction between them and then we apply some load like this, and then there are the contact area now will not be a single point, but a finite contact area, right. But what DMT model suggests is that if there is an attraction between them, so the attraction can be outside the contact area. So, to write it in little bit in magnified form, magnified image. So, in this region, let us say between in this region only. So, there is compression between them because of Hertz pressure. So, here it is compression, however, because of the Hertz load, right. However, in this region within certain distance there is attraction between them because of this intermolecular interaction, the adhesion forces between them. So, that happens. So, what is the load required to separate these two spheres, okay, in this situation? So, there is some fundamental difference between this DMT model and the JKR model. I will come to that in a minute, but what we discussed in the previous class, we discussed about this pull of load, and I derived that the pull of load can be given as F is equal to 2 pi r WA, and WA is the work of adhesion and R is that effective radius or relative radius or curvature of these two spheres. Now, so now let us say that we go back to this JKR model, where we have this, instead of rigid spheres, okay, we have now elastic deformable spheres. So, that we have. Now, in the absence of adhesive interaction between these spheres, as I said, it is the JKR, it is the Hertz model, it is the Hertz contact mechanics. The contact area between them when subjected to compressive load P follows the Hertz mechanics, okay, and we have derived it at A is equal to 3 Rp by 4 E star to the power 1 upon 3. So, A is the radius of the contact area, and then we have the load, that is contact load, that is P, that is there, and E star, for E star is this effective Young's modulus. So, remember that 1 upon E star we have derived it as 1 upon sigma 1 square by E 1 plus 1 up minus sigma 2 square by E 2. So, sigma 1 sigma 2, these are the Poisson ratios, and R is this 1 upon R is equal to 1 upon R 1 plus 1 upon R 2. So, this was that effective the relative radius of curvature. Now, here A depends upon P to the power 1 upon 3, that was the result that we had discussed. And then the centers approached by the center of the spheres approached by a distance delta, that we can show, this is from the Hertz model, A square by R. So, that is actually that we consider it is as the parabolic profile, the gap between these two spheres when they approach, and then the delta will be given as A square by R. And in presence of adhesive interaction between the spheres, okay, so from the Hertz, when you graduate to let us say the JKR, adhesion between the spheres, the JKR showed that the force required to separate these spheres, it will be P will be equal to 3 by 2 pi A into W. This is 2 pi R, yeah. So, it is 3 by 2 pi R into W like that. So, this is P F is equal to 3 by 2 P R W A, and we have discussed about all these things in lecture 23 this result, before that lecture 22, okay, we have this result, 21 also I think we have these results. So, there is in the JKR model we find that the adhesive, because of this adhesive interaction, the pull of force that is required to separate the spheres is F is equal to 3 by 2 pi R W A, and what is interesting is that this is remains independent of modulus, and so applicable to both rigid and deformable spheres. So, although the JKR model, okay, that is effective for deformable materials, right, but this pull of load, okay, as it derived it, okay, this is independent of the modulus. Okay. So, that means it should be applicable for both rigid and deformable spheres. So, for the rigid spheres in the DMT model, what do we get? We get F is equal to 2 pi W A. So, what it means? So, there is a confusion here, there is a contradiction here. So, for JKR result we get it F is equal to 3 by 2 pi R W A, and for DMT we get it 2 pi R W A. So, in this case there is no modulus, which is understandable because the sphere is rigid. In this case also this is independent of modulus, okay, although the spheres are actually deformable. Although there is a basic difference, okay, between this JKR and the DMT, the way they look at the contact. In the JKR, if you remember, okay, so there was this sphere and that was in contact with this, and because of this adhesion, what did you say? We said that the contact area that increases, and in fact we did not draw it exactly like this, we draw it something like this. When there was adhesion between them, we thought something like this, something like this. So, in the case of Hertz mechanics, we have this dotted line trace of these spheres. Okay, so, the contact was only this much. So, that was actually A0 here, and over here after this, because of this adhesion, the contact area increased to A1. Okay. So, this adhesion, okay, whatever was there within this contact area, okay, that was in JKR. However, in the case of DMT, what DMT thought that, okay, it is like this, because of, let us say there is some finite contact or whatever, if it is somewhat deformable, there will be a contact. However, because of this adhesion there is no deformation. So, this is the Hertz area, that contact areas that remains intact. Okay. There is no increase in this contact area because of this adhesion between them, although they are at the outside this contact area there is adhesion, that is interaction. So, there is attraction between the spheres outside the contact area. Okay. So, this interaction what is outside the contact area, that is not there over here, this outside the contact area. Okay. There is no interaction, no interaction, right, outside the contact area, outside the area of contact, that is in JKR, area of contact. However, that is not the case in the case of DMT. DMT model considers that there is attraction between the spheres outside the contact area. So, that is a basic difference, and this particular, so there was for quite some time there was a lot of discussion and then argument and counter argument between these two proponents of these two models and believers of these two models. So, finally, okay, Tabor, okay, he is also a mechanician. So, he resolved this in his 1977 this particular paper, and he said that, look, in the case of JKR there is a neck formation over here. So, as I was saying you that because of the Hertz mechanics, the contact area is only up to this A0, but because of this adhesion between these two spheres, the contact area goes to A1. But however, in this case there is deformation in these two bodies, two spheres, and there is a neck formation over here, and this neck is actually absent in the case of DMT. So, what did he say is that because of this adhesion, the neck that forms, okay, the neck height, okay, that can be shown to scale as something like this: R into WA, that is the work of adhesion square, by E star square whole to the power 1 upon 3. Okay. So, when this quantity, this neck height, the scaling of this neck height, okay, that it becomes higher, larger than the range of action of surface forces, means like these two gaps now, the gap between these two locations, surfaces, are actually quite large, okay, which is larger than the range in which the surface forces can act. Okay. So, that range of surface forces was written as epsilon. Okay. So, when this quantity is much greater than epsilon, that means this quantity is much larger than 1, okay, then you have the JKR model that is applicable. On the other hand, if this quantity is smaller, much smaller than epsilon, or somewhat smaller than that means this quantity is smaller than 1, then we have the DMT model. That is what Tabor said. So, when mu t is smaller than 1, okay, then we have the DMT model, then we should apply DMT model, because in that case the neck height, that is actually small with respect to this quantity epsilon, which is the range, okay, within which these surface forces can act, because you know surface forces are short range, and there is a limit within the gap between two plates or gap between two surfaces within which these forces can act, and that is what Tabor said, and that is the way he defined this particular parameter called the Tabor parameter. Okay. So, now let us take this problem to explain this matter a little better. So, let us consider a sphere of elastic modulus 0.5 megapascal, Poisson ratio 0.5, radius 2 millimeter, is contacted with a rigid flat plate. The work of adhesion between the adherent materials is 100 millijoule per meter square. Let us say the range of action of the surface forces is 5 nanometer, it can be little more than that actually. Determine if JKR theory can be applicable for obtaining the pull of load in the problem, in essence the mechanics of this contact, okay, whether JKR theory can be applicable. So, we need to estimate the Tabor's parameter here. So, the mu t will be equal to, so we need to determine the Tabor's parameter here, okay, which is defined as mu t is equal to 1 by epsilon and R WA, that is the work of adhesion square by E star square to the power 1 upon 3. So, let us put these numbers. So, epsilon is equal to 5 nanometer. So, I have written here 5 10 to the minus 9, and then R is equal to 2 millimeter. So, 2 into 10 to the minus 3, that is fine, and WA work of adhesion, okay, is 100 into 10 to the minus 3, because work of adhesion is given as 100 millijoule and square here, that is okay, and E star is E over E star, as you know, that is E over 1 minus sigma square. So, sigma is the Poisson ratio, that is 0.5. So, we know our some earlier problems we have estimated this quantity, this is comes out to be about 0.667, okay, into 10 to the power 6 is the megapascal. So, 10 to the power 6 Pascal and whole square and whole to the power 1 upon 3. So, you work out this whole calculation, it comes out to be 33. So, that means this mu t, that is the Tabor's parameter, is much greater than 1, and so therefore, JKR theory remains applicable. So, it is alright to use JKR theory in this case. Now, let us say that the diameter of the sphere is now decreased to 2 micron. So, okay, so it was say initially it was 2 millimeter, okay, a sphere. Now, I have got a particle in a sense, a spherical particle of let us say 2 micron. Then what happens? Then the Tabor parameter will be obtained as, instead of 2 millimeter, I have got 2 micron here, rest of the things remain same. So, here again epsilon, this is the 5 nanometer. So, that is the range within which the pull of load happens, works in this, let us say in this case also E star is 0.667 megapascal and work of adhesion is 100 millijoule, and if you work out the whole thing, it will come out to be this quantity, okay, here 1.675 10 to the minus 8 here and the minus 9 here, 5 10 to the minus 9. So, it gives us to 3.3. So, it is actually smaller. So, we can see that this Tabor's parameter mu t now has decreased to 3.3. So, it is still greater than 1, but it is not much greater than 1. So, we can say this, that mu t is greater than 1, but it is not correct to say that mu t much greater than 1. No, it cannot be said like that. So, that means that it is it definitely one cannot use the JKR model, but it is not clear if one can use this DMT model, because mu t is not small than it is little larger than 1. So, that issue is there. So, you have to see how to deal with such situations. Now, let us say that R is now made 2 micron and E star is now made 0.669 gigapascal. So, that means we have changed our particle modulus, particle material modulus. Let us say we have a particle much more the harder particle modulus is 0.5 gigapascal. Many metallic material or maybe some hard polymeric material can be of this order modulus. So, 0.5 gigapascal let us say, and again let us say the Poisson ratio remains same 0.5, right, and so therefore E star will be 0.667 10 to the power 9 pascal. So, here now I have got 2 into 10 to the minus 6 and here I have got 0.667 into 10 to the power 9 per pascal whole square, and now I see what that mu t it comes out to be 1.65 10 to the minus 10 here and 5 by minus 10 to the minus 9 here, and that leads to it having 0.033. So, now 0.033 is of course much smaller than 1. So, it is very clear case that the DMT theory will be applicable. So, what I see is this: when the particle size is small or the adherent is small, R is small, and also the elastic modulus is large, that makes sense, because DMT theory does not consider the deformation of these adherent bodies. So, it is a sphere, so it does not consider that it deforms at the surface. So, there is no deformation here, and that means only possible when let us say this elastic this material that we are discussing about, that is actually is soft, that is actually hard, that is it is difficult to deform it, and it has got a small dimension. So, for small dimensions here the particle size is also small. So, in this case it makes sense that the particle does not deform, and so it is more or less rigid, although it has got some finite elastic modulus, but it is more or less rigid for this adhesion purpose, and DMT is fine to DMT theory may be applicable, and we can correspondingly find what will be the pull of load, right. So, that is there. Now, so that is there, that is the DMT load, and the contact mechanics or the contact area, that will be determined by the principle of Hertzian mechanics, that is also there. So, if there is no compressive load in any region, so then there is no contact, the contact area will be 0. So, that is a thing. So, the contact area for the DMT model, that will be determined by the Hertzian mechanics, and pull of load of course will be that 2 pi and R and W A that we have derived a few minutes back. Now, how does this Hertzian DMT and the JKR pressure distribution look like? So, that is what we like to see now. So, the Hertzian mechanics, as we remember, so let us say it is like this. So, it is compressive. So, I will write the pressure. So, pressure is positive. So, it is Hertzian pressure will be something like this. So, let us say it is Hertzian pressure, positive pressure, maximum pressure applied. Yeah, it will be something like this, Hertzian pressure. For the case of DMT, the pressure will remain, Hertzian pressure will remain, right, in the contact. However, there will be a tensile in this region because it is opposite now, tensile, right. It is being this negative side, actually negative side. So, I do not know, I do not need to worry about these arrows anyway, negative actually basically. So, this is fine. So, this is will be, let us say this is the contact area A0 here. So, this is Hertzian, this is Hertzian, and this is negative this side because there is pull of load here. And then for the case of JKR, how will it be? JKR the contact, so contact area increases. So, there is actually contact area increases. So, it will be something like this. Actually, it is not infinity, it goes to infinity at the edge. So, it will go like something like this. Okay. So, it will be it will be something like this. So, the contact here is, this is within the contact area. So, I think I can do it better here. So, here for example, that this is the Hertzian contact, as we are saying, that this is the Hertzian pressure distribution. Hertzian mechanism only this. When you have this, when you have the pressure distribution is positive, in the negative side this is Van der Waals interaction. So, that is actually DMT pressure distribution, as I was saying, that it is attractive, okay, towards this, this is the flat surface. So, there is attraction. So, this portion it feels attractive here like this, and this portion, so therefore, this force is like this, attractive like that. And so, this is the same thing over here. So, the contact area this, and this Z0 is the minimum distance that is attained. So, when these two spheres, or like the sphere and this substrate, rigid substrate, okay, that comes in contact, let us say they come in contact, then what is the minimum distance they attain? So, when they come in contact, there is a minimum distance, that is Z0 over here. That Z0 is basically comes from the Lennard-Jones potential. Remember that it goes the something like this. So, there is an equilibrium distance that is there. So, after beyond this distance there is repulsion. So, in this portion, right, there is attraction, and beyond that there is repulsion. So, this Z0 corresponding to this equilibrium separation distance. So, when you are bringing these two bodies in contact, do not think that contact the distance is 0, no, there is a finite distance here, and that is this Z0, and that is determined by this Lennard-Jones potential, okay, when there are perfectly smooth surface. Now, for the case of JKR, as I said, that the contact area, the contact for this Hertzian part is this, and in this part in this part it will be something like this. So, here the in this portion there is attraction between them, there is attraction between these portions, between these two surfaces like that. So, there is like for DMT case, therefore, there is long range attractive force between these surfaces. Surfaces snap into contact when brought close and snap apart when separation. This kind of instability is there for the case of this DMT. So, I write like that. Okay. So, now let us do this exercise. In the given dimensionless contact area versus the dimension load plot. So, this is dimensionless load and this is dimensionless contact area. Okay. Identify the specific contact mechanics model. So, this contact area versus load plot describes these different mechanisms, right, JKR mechanism and then the Hertz mechanics and the DMT mechanics and all that. So, the question is that which one is what, that is what is being asked. So, now let us see, let us try to argue it. So, let us first think about this Hertz model. So, in the Hertz model, at the load is equal to 0, there is no contact, finite contact radius. So, actually as the load increases, the contact area should increase, and this is something. So, this is very clearly my Hertz model. Hertz model, right? And now, we saw that the pull of load that is required for the DMT model. For the DMT model, what was the pull of load DMT model? The pull of load requirement, the P was minus 2 pi r into WA. So, that was the pull of load. So, here you see pull of load for this particular curve, it goes to when the area becomes 0 at this load when goes to minus 2, okay. And of course, this is the no, this is made dimensionless and dimensionless by this quantity. So, P by 2 pi W is minus 2. So, this clearly is the DMT model therefore. So, this is DMT model. And then let us say for the JKR model, we know for the JKR case what is the pull of load. So, that is P is equal to minus 3 by 2 pi r W A. So, that is about minus 1.3 by 2, actually it should be minus 3 by 2 pi So, 3 by 2 is minus 1.5. So, it is pi r W A is used to make it dimensionless. So, the dimensionless load is minus 3 by 2. So, you see here that the contact area becomes 0 at minus 3 by 2 for this case, right. So, therefore, this particular curve has to be for the JKR model, And what is then in between this one, intermediate this one? So, now this is the intermediate case, and that is the issue here, that this Tabor's parameter help us in identifying that whether the situation, whether it is the DMT model that should be applied or the JKR model that should be applied, but it does not actually say that if both the models are not applicable, if the situation is an intermediate case like this, right. So, that is the point here, and that needs to be taken care of. So, we need to worry about this crossover from this DMT to JKR contact mechanism model, and that was taken care of by Moses, and he used this Dugdale model, okay. And I will just briefly go through it, and then I will discuss about it in more detail in the next lecture. So, this Moses Dugdale model, what he said is that of course, there is an attractive force in this region. So, that is outside the contact area, and he estimated, okay, he approximated this attractive force as a constant, okay, with respect to this gap between them. So, with respect to gap, this attractive force remains constant. So, this is delta, let us say gap, and this is the sigma, let us say, that is the attractive force between them. So, this sigma, it remains at sigma 0 constant, and if you remember in one of this previous lecture I had discussed about this Dugdale Barenblatt Dugdale model, okay, and where I said that there is a model here in which this attractive force that remains constant with respect to delta. So, Moses used this Dugdale model, and he considered that the attractive force with respect to distance, okay, that remains delta 0, sigma 0, and when delta c is attained here, then there is separation. So, he basically used this Dugdale model, and he did lots of interesting calculations and considerations, and there is this particular paper is a highly cited and excellent paper for adhesion scientist who wants to do as some advanced adhesion science work. I can read this paper, came in 1992. And so, that is the thing, you see JKR model came in 1971, this DMT model came in 1977, and then this JKR DMT transition Dugdale model that came in 1992, and I think in between this model of Tabor also came 1975, I guess, no. So, DMT model is even before that, yeah, Tabor model 1977, DMT model is I guess 1975. So, that was the way these things happened, and he came out with this particular parameter lambda, and then he drew this dimensionless curves, okay, p by again pi w r, and then this is the dimensionless contact area, and he shows from Hertz model to DMT to JKR with respect to different values of this quantity lambda, and that way he found out that it is a crossover from this DMT to JKR he described. So, I will take up this matter once again in my next class. Thank you.